All right, year 12. This is where we left things in class today. So I thought we'd pick things up. I'm not going to see it till Thursday, and I couldn't just leave things where they were. Besides which, we've got a few things we need to cover before the end of term, and it's too long to wait with your Group 4 day or whatever's happening on Wednesday. Okay, so I'm just going to remove what I've started to do here, all right? Okay, so just to bring you back to where we were at the end of class, we're looking at different representations of complex numbers. We know about the rectangular form and the mod arg form. Now, what we looked at in class today was this incredible process of polynomial interpolation, where we took our sine x and our cos x, and in fact our e to the power of x, which are not polynomials, and look to make polynomials that are exactly the same function. All right, this is a crazy thing, and they're called Taylor series, and they're infinite series, infinite sums that lead to the exact same function. Right? They track perfectly. All right, so we had a look at some examples and in using Desmos, but and this particular one over this side, this is our even functions, and even functions map cos quite nicely because cos x is an even function. So this was cos x, and our odd degrees here, they mapped our rotational symmetry that is a feature of sine x. And okay, so we looked at and we did, in fact, and it might be worth writing down here what our sums were. So we'll just do that. We talked about this one here, cos theta. We talked about cos theta, just looking for an appropriate color. Cos theta, excuse me, or cos x. Now I've written theta here, and then I've turned that into x. So that's a bit confusing, isn't it? So perhaps I'll just change here to x so that we're being consistent, but obviously that's interchangeable, and in this case x is the angle sine x. So looking at cos x, therefore, we're saying it's equal to, not just approximately, but equal to the infinite sum from n equals 0 to infinity. Now, how do we represent this? This was a minus 1 to the power of n, and then we wanted x to the 2n to cover the even powers over 2n factorial. Isn't that right? So that sort of described this infinite sum here, because I can't, wherever I stop, it's not gonna match it perfectly. And over here we had sine x, and we determined that sine x was the infinite sum from n equals 0 to infinity with an alternating sign, negative 1 to the n. Now, did we have x to the 2n plus 1 to cater for our odd function over 2n plus 1 factorial? Now, just check that this works. N equals 0 looks pretty good. When n equals 0, actually, yes, we get x to the 1 over 1 factorial, and that's good. And when n equals 1, we get x to the power of 3, and it's negative. So that looks fine. And over this side, x to the power of 0, x to the power of 1 looks good. When n is 2, it's good. Yep. So that's there are representations, our Taylor series for cos x, sine x, and in fact up here, e to the power of x. E to the power of x. Here, now we can represent e to the power of x as, because it's just a nice, neat way of doing it, isn't it? If we can write it as a sum from n equals 0 to infinity. And what are we picking up here? We don't need an alternating sign, so all we need to do is represent our x power by n, and we're popping it over n factorial. So at n equals 0, it's 1. At n equals 1, it's x. When n equals 2, it's x squared over 2 factorial, etc. So that neatly encapsulates what we have there. All right, that's e to the power of x. So they're our three Taylor series that we came up with in class, and we're attaching now those polynomial sums to cos x and sin x in here, and I left you with this task. I left you with the task of running that expansion out. Something not quite right about this one at the moment, cos x plus. Running that expansion out and then gathering in ascending powers of x. All right, so let's start to do that now. Maybe you've had a go at this and are ready to compare notes with me. So we've got an r at the front here, which is kind of annoying, but we've just got to let it sit there. Now cos x is here, and this is I sin x. All right, so this is sin x over the right side, but all those terms have to have I distributed through them. All right, so I'm going to take that into account when I run this expansion out. So in ascending powers of x, I've got 1 here. I don't need big square brackets. 1. Now, what's my next power? It's x, so it's plus x. Oh no, it's not plus x, it's plus ix. ix. My next power is x squared over 2 factorial, and it's minus. Then we bounce back over this side to pick up the x cubed. It's also minus, but it's multiplied by I, so it's ix cubed over 3 factorial. All right, let's pick up the pattern here. Let's keep going. We're now on x4, and it's plus. My even powers don't have any i's attached to them. Over here for power 5, and I've got a plus ix to the power of 5 over 5 factorial. So you can see we've got i's attached to the odd powers, not to the even powers, and our signs seem to be going minus, minus, plus, plus. Does that continue? When I go to x to the power of 6, yes it does. I've got x to the power of 6 over 6 factorial, and then I've got minus again over here, ix to the power of 7 over 7 factorial. So plus, plus, minus, minus seems to be the pattern. All right, I may as well just get another couple out. X to the 8 over 8 factorial. It's probably a bit of overkill, but I'm having fun. It's another plus here. It's ix to the 9, odd power over 9 factorial. And this just goes on. All right, that goes on. All right, good. So we've got them in ascending powers of x. What now? Well, you know what we're trying to do. We're trying to get it looking like e to the power of x. And okay, and that's why we wanted ascending powers, so we can start to see how it takes shape. But there's a problem here. We've got alternating signs, and we've got this I in there. What's the I doing in there, right? So that's also something we need to consider. Righto, so let's get to work now on this. And I want to maybe think about removing my signs. And in fact, yeah, I want to start thinking about making these all positive in some way. So let's think about this, how we can write this in another way. So can I write this as 1 plus, and I'm going to write this as ix over 1, okay, because that's ix to the 1. It's I to the 1, x to the 1, if you like. Now, this x to the power of 2 over 2 squared, I'm going to do something here because I want to actually introduce an I to every term. Now, all right, and I has this magical quality where, all right, I to the power of 1 is 1, is I squared is negative 1, I cubed is negative I, and I to the power of 4 is negative I times I, so it's negative I squared, negative negative 1, back to 1. All right, so this is a really important little for sequence that I'm going to tap into now. So, all right, I'm going to use the fact that I squared is negative 1 to counter this negative here. So I'm going to write this, rather than minus x squared over 2, I'm going to write plus I squared, because that's negative 1, x squared over 2 factorial. Now I've done two things there. I've turned the negative into a positive, and I've matched my I power with my x power. Let's see if I can keep doing that. I also want this to be a plus. Now my I, I've got an I here, so that's all good, but I want my I to match the power of the x. And can I do that? I cubed is negative I. I've got a positive I here, but if I make that I cubed, if you like, what I'm saying is, if I make this negative here I cubed, I'm making that minus I, which is going to change my sign here. So I cubed x cubed with a plus sign out the front will give me the same result. That's over 3 factorial. Think about this. I cubed, that's equal to negative I. I've got the results over here, so we don't have to keep those. We don't have to keep remembering those. I cubed is negative I, which is what I have here. I've just got minus ix cubed, and I've changed it to plus I cubed x cubed. Same thing. All right, but what I've achieved is all plus and powers of I matching powers of x. All right, let's see if we can keep that going. X to the power of 4 over 4 factorial. Well, I've got everything looking pretty sweet there. I've got a plus in place, but I don't have any i's. Well, I to the power of 4 is 1. So whacking an I to the 4 in here doesn't change a thing. I can put an I to the 4 in front of anything, and it's not going to change its value. And it's going to help me out here. It's going to make this one look like every other term. Now, are we getting the hang of this? I x to the power of, what's I to the power of 5? Well, I to the power of 5 just loops back around here, and I to the power of 5 is just I. Well, I to the power of 5 and I are the same, so I can just write, rather than I can write I to the power of 5. Okay, because I to the 1, I to the 5, I to the 9, I to the 13, they're all got the same value. So I to the power of 5, x to the power of 5 over 5 factorial. And now, are we happy that this is just going to keep rolling out? All right, I to the power of 6 is that equal to, does that cover my negative 1 here? I to the power of 6? Sure it does, because I to the power of 6 is the same as I squared, or the same as I to the power of 10. It works in a sequence of 4. So that's over 6 factorial, and we continue on our merry way. Okay, we get the idea. This looks good. So now, in fact, I can, I've come a long way here, haven't I? Now, this looks really nice. Can we write this one step better? All right, ix, right, this is 1 plus ix over 1 factorial. Now, this I squared x squared, we can write that as ix all squared over 2 factorial plus ix all cubed over 3 factorial. Okay, ix all to the power of 4, you get the idea. Again, what we're doing here, ix all to the power of 5 over 5 factorial, ix to the 6. All right, this pattern continues. Okay, now how does this compare to e to the x? Well, if we just have a look now, if we just take a little glance up at e to the x and imagine e to the minus x now. So let's have a look at, all right, so now e to the minus x, what's that going to look like? So I've got e to the x, it's 1 plus x, but that's going to be ix. Sorry, this should read e to the ix. So if e to the x is equal to this, e to the ix is going to be e to the, we're just going to now pop an ix wherever we see x. So x squared becomes, right, that x squared there becomes ix squared over 2 squared. So it becomes this, ix all squared over, not 2 squared, 2 factorial, plus not x cubed, but ix cubed over 3 factorial. And it seems to be matching up with my expansion of my mod arg form. And I'll just go to 6 because that's how many I've got there. That seems to be rolling out nicely. So have we established some result here? So can we say therefore that z equals r cos theta plus I sine theta? Can we say that's the same as? So we've worked this all the way down here, and we've matched it up now with what's written in green, which is e to the power of ix. So the polynomial interpolation for cos theta and the polynomial interpolation for sine theta have been substituted into my mod arg form. My polynomial interpolation for e to the x has been rewritten with e to the ix, and it matches exactly cos theta plus I sine theta. So can we therefore say that my complex number z can be written in this form? Z equals, I've forgotten the R there, RE to the IX. This is known as Euler's form, Euler's identity, and it leads to one of the most beautiful results in all of mathematics, in fact, all of science, in fact, all of the world. If you Google the most beautiful identity in the world, this will pop out of everywhere. Not this, because we've got to apply a specific case to this. So what we've got now is Euler's identity, RE to the IX. It's just another way of representing the complex number z. So for instance, z equals, let's say, I don't know, what do we like to work with? 3 plus 4i. All right, so that's got a modulus of 5. You know where it is. You can sort of picture it on the Argand diagram. It's 3 across and 4 up. There it is. Okay, we can write that as, actually, I should have, why don't I write 4 plus 4i, and then I can use a, all right, so 4 plus 4i, so it's now 4 across and 4 up. So I now can represent this using my argument of pi over 4, is that right? And my my modulus as the square root of 32, or what's that, 4 root 2. So I could write this as 4 root 2, 4 root 2 being this distance here, 4 root 2, square root of 32, 4 squared plus 4 squared, 4 root 2 cis pi over 4. That's my mod arg form. Okay, so now I've got it written, the same complex number, z, I've got it written in rectangular form, mod arg form. Now I've got another form I can write it in. I can write it in Euler's form. So I can write it as, how would I represent it? R still being this distance here. So 4 root 2 e to the power of I. Now we've got x here. We've been using theta everywhere else. So let's now replace with theta. So re to the I theta. So I would just write in here 4 root 2 e to the I pi. That's the same complex number. So what does all this mean? Okay, so if we have a look at a specific, I'll just get rid of all this. If we have a look at, just like we did there, let's have a look at another specific complex number. Let's consider z equals -1. Okay, z equals -1. Let's look at -1, that position on the Argand diagram. It's just over here. Now we could write that in mod arg form as, what would we write? 1 cis pi being my argument, and 1 not necessary. Let's write it in using Euler's identity. Right? We could write it as 1 e to the I pi. Okay, so z equals 1 e to the I pi. And z is -1. So I could write this equals -1. Okay, so let's just tidy this up a bit. This says e to the I pi is equal to -1. We are almost there, ladies and gentlemen. If I now just add 1 to both sides, I have e to the I pi plus 1 equals 0. And there we have it. That is the most beautiful identity in the world, bar none. Now look at what we've got. The reason it is afforded such status is this. All right, it's obvious to you, but I'm gonna point them out anyway. If you look, we've got 5, 1, 2, 3. We've got 5 elements to this, and they all have monumental importance in mathematics. We have 0. All right, 0 is obviously a pretty important number for us in our system. All right, it's the additive inverse, not the additive inverse, the additive identity. So, right, you can, x plus 0 is still x. Number 1, well, that's got lots going for it, but in the same sort of spirit, it's the multiplicative identity. Just one thing about it. E, what about E? He's huge. He is our constant of exponential growth. He is our constant of exponential growth. Right? That's it's the function that doesn't change upon differentiation. E is of huge importance. So you take this constant of exponential growth, you raise it to I, which is equal to the square root of -1, and introduced us to another world of numbers that were only considered when cubics were looked at being solved. So that's up there in the index of our constant of exponential growth, along with the product of I and pi being that hero of circles, where so pi being the ratio of the circumference to the diameter. Circumference divided by the diameter on a circle. These are 1, 2, 3, 4, 5 of the greatest superheroes in mathematics, all combined into one beautiful identity. E to the I pi plus 1 equals 0. So that's what all this was. That's what all this was in aid of, reaching this moment. Now I could have just popped that like the textbook did into a box and said, here it is, Euler's identity. But it was too good to miss out. So that's the end of that story. That's that's our third and final representation of a complex number, and certainly the most interesting. All right, let's go. I'm now going to look at some couple of examples. I can work through a couple of examples. Then I'm going to leave you to do exercises 12C and 12D. All right, let's work through a little example here. We've got two complex numbers, Z1 and Z2. Now, Z1 is in mod arg form, Z2 is in Cartesian form. And we want to be able to switch between the two. So what we're doing in the first instance here is we're going to look at changing Z1 into Cartesian form, 3 cis pi on 6. Okay, so where is this on the Argand diagram? I always find a little visual helpful. Pi on 6 is, or perhaps it's making a little angle here of pi on 6, and our distance, our modulus is 3. So here's my Z1. How do I represent that in rectangular form? Rectangular form meaning just xy at right angles, forming a rectangle. Okay, so I need to know these distances here, don't I? I need to know this distance and this distance as my x and y, so that I can represent in Cartesian form. Okay, so I need to know what cos and sine of pi on 6 is. So I remind myself of what pi over 6 is, and that's that little angle up here, isn't it? And this triangle is half of my equilateral. They're my side lengths. Oops. They're my side lengths. So I can see that cos of pi on 6 is equal to root 3 on 2. And sine of pi on 6 is equal to 1/2. So that means that x over 3 is equal to root 3 over 2. So I'm going to come down here and I'm going to say, righto, so from here I can say that root 3 on 2, which is my cos pi on 6, is equal to x over 3. So therefore, x is equal to 3 root 3 over 2. And we come over this side and we'll say that 1/2, which is sine pi on 6, 1/2 is equal to y over 3. 1/2 is equal to y over 3. So therefore, y is equal to 3 over 2. So we now have our x and y, so we can now represent Z1 in Cartesian form like so. So I say, therefore Z1, what's that? So Z1 is equal to 3 root 3 over 2, 3 root 3 over 2 plus 3 over 2 I. Now my second task here is to express predictably Z2 in polar form or mod-arg form. So we would write Z2 therefore as, right, so we need Z2. What's Z2 look like? 5 plus 5i. So Z2 is 5 plus 5i, so hanging out here somewhere. And we want to know, for mod-arg form, we want to know what our theta is, and we want to know what r is, don't we? So if this is 5 and this is 5, then r is equal to the square root of 50, or 5 root 2. 5 squared plus 5 squared, root 50, so 5 root 2, and our theta, given that x and y are equal, is pi and 4. So therefore, Z2 will equal 5 root 2 cis pi over 4. 5 root 2 cis 5 over 4. Okay, next question. I'll write it now. We're calculating Z1, Z2 now, but in both Cartesian and polar form. So calculate Z1, Z2. So we're looking for the product. Giving your answer in both Cartesian and polar form. Okay, so Z1, Z2. Now, if they're in mod-arg form, it's dead easy. So Z1, Z2. So let's just consider separately. So, all right, in polar form. So we're going to write it as Z1, Z2 is equal to, now Z1 is 3 cis pi on 6, and Z2 is 5 root 2 cis pi on 4. So it'd be 5 root 2 cis pi over 4. So what do? We multiply the moduli, so we end up with 15 root 2, and we add the arguments. So we end up with 4 pi plus 6 pi, so 10 pi over 24, or 5 pi over 12. Okay, now in rectangular form or in Cartesian form, we are going to start with them in Cartesian form. So it's, what do we end up? What do we get? Okay, so 3 root 3 over 2 plus 3 root over 2i. 3 root 3 over 2 plus 3 over 2i. That's our Z1, is it? And Z2 is 5 plus 5i. So just do a distribution here, or a multiplication. So we would write this 3 root 3 times 5, so 15 root 3 over 2. Now we're multiplying by 5i, so that's 15 root 3i over 2. Now we add 3 over 2 by 5, so that's 15 over 2i. And then we've got 3 over 2 times 5, which is 15 over 2. I squared is -1, so that's minus 15 over 2. Okay, so collecting now our real parts. So 15 root 3 minus 15, it looks like, over 2 is our real part. And our imaginary part is 15 root 3 plus 15 over 2 with an I hanging off the end there. And the last part of this example is to ask, find the exact values. So hence is an important word here. Hence, which means we've got to use what we've just found. We can't just charge off in a different direction. Hence, find the exact values. Find the exact values of sine 5 pi on 12, cos 5 pi on 12, and tan 5 pi on 12. Okay, so how to do that? Well, we've got 5 pi on 12 whacked in here to our polar form, haven't we? So we know that this polar form here, so we know that here, this equation and this equation, they're equal. So what we can do is, okay, so by matching our coefficients is how I think we'll end up with these values of sine, cos, and tan 5 pi and 12. So let's have a look at that. Therefore, right, so we can therefore say, I've got two versions of the product here. So 15 root 2, and then it's cis, so cos 5 pi over 12 plus I sine 5 pi over 12. That's equal to this thing here, 15 root 3 minus 15 over 2 plus 15 root 3 plus 15 over 2I. Okay, so equating imaginary and real parts. What we'll end up with is the real part over here is 15 root 2 cos 5 pi over 12. That's going to equal the real part on the right hand side, which is 15 root 3 minus 15 over 2. So we end up looking at solving this. We get cos of 5 pi over 12. So making cos 5 pi on 12 the subject, we've just got a little bit of arithmetic to do with our surds over here. We're going to divide by 15 root 2 or multiply. So that's actually just going to turn out to be, I'll just multiply. So multiply both sides by, what am I talking about? 2 root 15 over 2. So I'll get 2 times 15 root 2, so 30 root 2. I'll try and make sense in a moment. If I multiply this by root 2 on root 2, we will get 15 root 6 minus 15 root 2 over 60, which is equal to root 6 minus root 2 over 4. So that's the exact value of cos 5 pi over 12. So root 6 minus root 2 over 4. So we can continue now with the sine 5 pi over 12. It'd be great for you now to pause the video and do this one yourself, just equating the imaginary parts to both sides of this equation. So sine 5 pi over 12 here will be equal to 15 root 3 plus 15 over 2. Now I'm going to divide by 15 root 2, so it'll be 30 root 2 here. Multiply by root 2 over root 2. And we'll get 15 root 6 plus 15 root 2 over 60, which is root 6 plus root 2 over 4. Now tan 5 pi over 12, pause and do. You're just going to do it as a sine divided by cos. So that'll be root 6 plus root 2 over 4. I'm going to divide by root 6 minus root 2 over 4, or multiply by its reciprocal, root 6 minus root 2. So we end up with root 6 plus root 2 over root 6 minus root 2. I'm going to multiply now by the conjugate. To get, what do we got here? 6 plus 2, so I'll get 8 plus 2 root, what do we got? 2 root 12, and root 12 is 2 root 3, so that'll be 8 plus 4 root 3 over 6 minus 2, which is 4, so I'll end up with 2 plus root 3 as the exact value for tan 5 pi over 12. Now you can go ahead with exercise 12C and complete that exercise. Okay, we're now going to look at division of complex numbers. All right, so here's our Z1 and Z2 in their general format. Now remember, recall that Z1 times Z2 will equal, multiply the moduli and add the arguments. For division, we have the result Z1 over Z2. No surprises, but it's equal to R1 over R2. All right, so divide your moduli. Cis, and I'm sure you'll guess it, theta 1 minus theta 2. So we add for multiplication, subtract, as we do with so many elements of mathematics. That's completely consistent. Okay, some examples. Okay, here we are, a couple of examples. Z1 and Z2 given to us in two different formats. So Z1 over Z2 in part A here. Right, so R1 over R2, my R1 and R2 are given to me here as the moduli of Z1 and Z2 respectively. So it'll be 6 over 2 cis. Now what are we doing? We're taking 75, which is my argument of Z1, yep, and subtracting 20, which is the argument of Z2. So that is clearly 3 cis 55 degrees. Okay, part B, Z1 over Z2 here. Z1 over Z2 will equal 8 over 4, so 2 cis. 2 cis. Now we're taking 5 pi on 7 and subtracting pi over 3. So we just need to simplify that. It's 15 pi minus 7 pi, so that's 8 pi over 21. Okay, practice to be had in exercise 12D, and I imagine that we can do all those questions. See you soon.